Okay guys, in previous videos we've been looking at angles in standard position, and after doing so it actually becomes very convenient to describe the motion of things moving around in circular paths using these ideas of central angles. And so that's what we're going to kind of look at in this video, is these two topics, or these two concepts of angular velocity and linear velocity. And specifically what we're going to be looking at is what we refer to as rotational trig, things spinning around a central axis. And so examples of things that do rotate about central axes, these would be things like tires, Ferris wheels, washing machines, records, the earth, okay? But when we look at things spinning around a central axis, we could almost represent this, two-dimensionally as really a circular path where maybe we have an object located around the outside, and what's happening is it is put in motion, and we'll call this uniform motion. That is to say that it's always going the same speed. But maybe what our job is to describe to an audience how fast this object is moving around this outside of this path right here. So if we call this point 0, where it started, its initial point, and it navigates to point 1, how could we describe the path of this object as a speed? And so when we talk about speed or velocity, we tend to describe how things change over time. And so the two types of speed we're going to tend to look at today refer to two different types of measurements we look at in central angles a lot of the time. But the very first one we're going to look at is this idea of how fast is our rotation changing over time. And we're going to give this a name. We're going to refer to this as angular velocity. So that is to say, the ratio of the change in the central angle to the time required for that change is given by this Greek letter curvy W, or in other words, what we're going to write here is omega. This undercase letter or lowercase letter omega represents how fast our angle is changing over time. So if you've ever seen something that's like, you spin 360 degrees every second, that would give you an idea of how fast you'd be rotating around. Every second you're making one full rotation around this thing. So again, we talk about angular velocity. It is our change in angle over the change in time, where we say omega is in radians per unit time and theta must be in radians. Now the other type of velocity we're going to look at, or tend to look at, is looking at the change in distance over time. And this is our traditional sense of velocity here, distance over time. But when we talk about the path of an object moving around the outside of a circle here, we're saying that the distance that it's covering is equal to this idea of the arc length that it is covering here. And so given a circle of a radius r with the central angle theta and this arc length that it's covering here, we could say that its linear velocity is given as its distance over time, but in this case that's given really as our arc length over time. And so that's going to be our second type of velocity that we measure of circularly moving objects here, linear velocity. And we say that this is the ratio of the change in arc length for an object to the time required for that change. And you can see here that we define this as being arc length over time. So linear velocity is arc length over time. But I also want you to notice that because we know that, in radians, generally speaking, the number of radians an angle equals in measure is equal to the number of times a radius goes into the arc length. Remember that this led us to our arc length formula of S equals R times theta. That is to say that if we take the radius times the number of radians our angle is here, we would have the distance on that arc length. So another way to write our linear velocity is also V equals R theta, or theta R over time, because that would be our arc length over time. So what we're going to do is we're going to look at a few instances where we look at some of this rotational trig and how we might apply these two sets of formulas here, angle over time or arc length over time. So before we do that, what I want to kind of start with is just this idea of angular displacement. Because both of these formulas that we use here for linear and angular velocity require us to have our angle in radians, a lot of the time what we're going to have to do is convert our angles into radians. And so we're going to talk about angular displacement is the amount of angle you rotate through, and we'll define this as the amount of angle that an object rotating about the center of a circle rotates through. So your angular displacement is the amount of angle that you rotate through, and this is always in radians, or preferably in radians. So to find angular displacement, I would write this little formula down, but what we do is we multiply the number of RPMs by 2 pi, or I'm going to say generally speaking, what we're going to do is take the number of rotations, okay, times 2 pi, because what do we know? Well, we know that every one rotation is 2 pi radians, and so to say the number of radians you rotate through, it would always be equal to the number of rotations times 2 pi for each rotation. That would convert it into radians. So as an example, I give here, it says, what is the angular displacement for an object that rotates through 5.5 revolutions? I would say that my angle, first of all, and I'm going to write this down as 5.5 revolutions. But essentially what we're going to be doing here is taking this times 2 pi, and what I really want to do is drive home the fact that this is really a conversion. So when we take it times 2 pi, what we're really saying is we have 2 pi, and I'm going to write in radians, per 1 revolution. And what you're going to see is that our revolutions in terms of units cancel out, and what we get left with are purely radians units here. But common sense would tell us, 5.5 revolutions times 2 pi, that would give us the number of radians here. And I'm actually going to find this. We're going to say 2 pi times 5.5. So we would get 34.56 radians, or I suppose in this case I can say 11 pi radians, or about, and we said 34.56, so 34.56 radians. So first things first, we just want to be know that we are comfortable with finding the number of radians that we rotate through given a situation. One thing that's worth mentioning here is this idea of RPM, so we can write this down right now, but if you've not seen RPM before, RPM is a fancy way of writing revolutions per minute or rotations per minute. So we'll get this in here. But make sure that you do write that down because we're going to be taking that times 2 pi to convert into number of radians per minute. So let's take a look at a couple of examples here that I've got. And I want to start with our angular velocity example. So angular velocity, let's go ahead and start with the fact that our angular velocity is omega, is really just our number of radians we rotate through over a given time. So for example 1 here, it says find the angular velocity. We want this in radians per second for an object that makes 4 revolutions every 19 seconds. Now, as far as finding angular velocity goes, that means go find omega. It must mean that I'm also telling you your angle and your time. So my number one recommendation for anybody doing these types of problems is to write down the information you need for it first. So I'm going to write down my angle here, 4 revolutions. And I'm also going to write down my time as 19 seconds. So as far as piecing this together goes, we just need to put our 4 revolutions over 19 seconds, but remember that our angle theta has to be in radians. So this is where we're going to take our 4 revolutions times 2 pi, or times 2 pi radians per 1 revolution, and our revolutions cancel out. So we get 8 pi, and this is in radians, so we can write rad, or we can just write 8 pi. But it means that we have our angle here, and we have our time. So if we want to have our omega, all we're really going to do is take our angle, which is 8 pi. I'm not going to write the word, actually I will write rad here. 8 pi radians over 19 seconds. So our job is to find this in radians per second. The neat thing here is we can just go ahead and say that it's 8 pi 19ths, and then we toss the units off on the side. And that is to say that this would be the number of radians per second, and something that we certainly would want to find is a decimal. So let's go ahead and do that. We say 8 pi divided by 19. This would be the same as saying we are going about 1.32 radians per second. So 1.32 radians per second. So you can see that when doing these problems, really we're looking at our formula and saying we need theta and time, but just writing those things down and substituting them in as long as your angle is in radians. So let's take a look at another example of angular velocity here. It says find the angular velocity in radians per second, okay? For an object rotating at a rate of 200 RPM. Now, again, since we're finding angular velocity, I need theta and I need time, and we're going to write down both of these right here. But in terms of theta, this is really interesting. What this says is 200 RPM, which is telling us 2 bits of information. It's going 200 revolutions every 1 minute. So this is kind of like a nice way of writing things because it does tell us these 2 bits of information in one little small datum. But we can split this up here, and again, we want to make sure that we have the number of radians here. So we're going to take this times 2 pi radians per revolution, and we get 400 pi radians, okay? We'll write that in. But this would be our number of rotation radians, and then our time. Let's go ahead and set this up here. Our omega then is going to be 400 pi. We'll go ahead and write rad. And this is over 1 minute. Okay, so here, we could say is really, if we want to do that thing again where we say 400 pi over 1 radians per minute, this would be our angular velocity. The rub here is that I want this in radians per second. So before we go writing this as a decimal, what we're actually going to do is convert this into the units that we want, which is radians not per minute, but radians per second. And the way this works is we're just going to multiply by conversion factors to get our minutes to drop out. And so minutes to seconds, what do we know about minutes and seconds? So I know 60 seconds in 1 minute. But what I'm going to do is I'm going to make sure that I multiply by 1 minute on top over 60 seconds. And the reason why I'm doing this is because it'll get my minutes to cancel out. And you can see now what I'm going to be left with is radians per second, which is exactly what I want. So multiplying straight across, we get 400 pi times 1, which is 400 pi, and this is in radians on top. And this is all over 1 times 60, which is 60, and that's 60 seconds. So we can really say that this is 400 pi 60ths, and this is radians per second. So let's go ahead and, traditionally we would simplify something like this here. As a matter of fact, I'm going to go ahead and do that. It would be 40 pi over, let's see, 6. And that would be the same thing as 20 pi over 3. 20 pi over 3 radians per second. And while we're at it, let's go ahead and make sure that we get a decimal here. So we would say, just using the original, since I am open to making mistakes here, 400 pi divided by 60. This would mean that we have about 20.94 radians per second. So about 20.94 radians every 1 second. This thing must be zipping around pretty fast. Okay, so let's take a look now at some linear velocity and kind of contrast it with our angular velocity here. So our linear velocity example, this is only slightly different in that our linear velocity is not angle over time, but it's arc length over time. And truly the form of this formula we want to be using is theta r over time, because our arc length is really theta times r. So this means that when doing these problems, we kind of need 3 bits of information to find our linear velocity. We need our theta in radians, we need our radius length, and we need our time. So looking at this as an example, it says a carousel contains 3 concentric circles of animals. The inner circle of animals is 11 feet from the center, and the carousel makes 2.65 radians per minute. Determine the angular and linear velocities of someone riding on the inner circle and the outer circle. So let's start with our inner circle here. We need our angular velocity first. And what we know about our angular velocity is its angle over time. So in this case, I suppose we need 2 things. We need our angle and our time. In this case here, our angle is given by 2.625 revolutions. And our time, well, I suppose this is rotations per minute. So this is in 1 minute. Okay, so looking at our angular velocity here, making sure that we're converting this into radians first, we'll take this times 2 pi rad. Our angle, get my calculator out here, 2.625 times 2 is 5.25, so we get 5.25 pi rad. These are our 2 initial measurements here. Let's go ahead and load these up. And so I suppose our 5.25 pi rad for 1 second, or 5.25 radians per second, would be our angular velocity here. And we can go ahead and get this as a decimal, so we say 5.25 pi. We get about 16 point, well, we're going to go 16.5. So 16, oops, I will put that, sorry, up here, 16.5 rad per second. Now, when we go back to look at angular velocity, I'm trying to fit all this in here. Angular velocity is a little bit different than linear velocity in that what we're going to do a little bit differently this time is we're going to take our angle times our radius length over our time. And what this, I suppose, means is all we're really going to do is add in a factor of our radius. So we still have 5.25 pi radians. And we also know that 1 radius length here for our inner part of the circle is 11 feet. And this is all over 1 minute. So again, if we want our linear velocity, and let's assume we want it in minutes, we don't have to convert this now. I suppose I could just take 5.25 times 11. That's 57.75. We have 57.75 pi radian feet, or in other words, just feet, per 1 minute. This would be our linear velocity. And so I'm going to go ahead and find this as a unit rate here. If I take 57.75 times pi, which we had a factor of pi in there, we get about 181.43. So 181.43 feet per second. So what we're going to do now is kind of contrast a person on the inner part of this carousel with the person on the outer part. What I want you to notice is the angular velocity. The angular velocity, if we talk about the outer portion, it doesn't change. The angle of a person rotating around the outside portion is going to stay the same, but their linear velocity will change. So that is to say that they're still going 5.25 pi rad every 1 minute. And so this is our approximately 16.5 radians per minute. But when we look at linear velocity, the thing that's changing this time is that we have our factor of our radius is a little bit bigger. That is to say that we still go through 5.25 pi radians for our angle here, but our radius becomes 20 feet. If you look at this diagram here, 20 feet, and this is in 1 minute. So how much of an impact does this make here? Well, if we take 20 times 5.25, 20 times 5.25, we get 105 pi rad feet which is really just the same as feet since radians are unitless, and this is per 1 minute. And so to convert this into a decimal now, I suppose we would get 105 times pi. That would give us 329.9, so 329.9 feet per second. So in terms of how much faster is somebody traveling on the outer portion than the inner portion, we could just do some simple subtraction here. If I take off that 181.43 feet that a person on 11 feet from the center is traveling, a person on the outside is going to travel an extra 150 feet per minute just because they are further from the center. So looking at linear and angular velocities, kind of looking at what they are, know your formulas, and then just know that you need theta r and time, making sure that theta is in radians whenever you do these calculations. Cheers.